Okay, so welcome back for video number 2, where I'll solve a simple first order circuit problem as requested in the comments in the last video. This is a really simple problem just to show you the basic process and get you started. So here I have a circuit I just came up with like 2 minutes ago, and I just gave a simple prompt: find VC of t for t greater than 0. So VC indicates we want the voltage across a capacitor, and the problem, it's been given here, VC plus or minus, and it's a 100 microfarad capacitor. We see there's a switch, and it goes from this position over at t equals 0. We have two voltage sources, but the basic gist of the problem is we want to find VC at t. Now, because the voltage we're looking for is the voltage across our energy storage component, we can use the equation that we would have learned in lecture, or that I have over here. I'll make sure I write it down correctly. So VC at t, and in a problem like this, it'll follow this basic form. It'll equal VC at infinity plus VC, and at the switching time is important. I'll call it T0, T0, minus VC at infinity, E negative T minus T0 over tau. Important things to know: tau is equal to RC, and it's dependent on the structure of our circuit. T0 is a switching time. So when does the switch activate? Because in some problems, your switch might not switch at time 0, which will cause you some problems in your math. So T0 in this problem is 0, so it makes it a little bit easier on us. RC, C is just the capacitance. R will come from what does the capacitor see as in terms of resistance when the circuit is in its, I guess, let's call operating mode, when the switch is closed. Now, we'll have to do almost like a Thevenin circuit to find that. It's the equivalent process of finding R Thevenin. But first, let's look at what we need in our equation. So VC at 0, that's something we have to find. I'll use different colors because I have different pens. VC at T0, we have to find that. And the last thing we'll need is the tau in red. So the first thing we should look for is actually the VC at T0 at my switching time, because that's the basis of the problem. VC at T0, in this case, equals VC at time 0. Now in my problem, the switch is at T0. So for a capacitor, VC at 0 minus equals VC at 0 plus. This equation is important because the voltage across the capacitor is continuous, so it can't do any jumps. So when we flick the switch, the voltage it had before the switch flicked will be the same as the voltage immediately after, given here. So to find VC, we'll call it 0, but 0 plus, we need to find what was the capacitor's voltage before the switch happened. Now this is important because this is time less than 0, which means it's before the switch activated. So let's draw the circuit and see what we have. And I have no connection there, that's open. 10K. Okay, so this is our circuit. Now, I want to find what's VC. And actually, the time T0 is, we assume, steady state. So we want to say the switch has been closed for a very long time. The switch has been closed since T negative infinity, or like it's just in steady state. What it means is this circuit's been in this shape long enough that nothing is changing anymore. The capacitor is either fully charged or fully discharged, which means steady state. This indicates that the capacitor becomes an open circuit. and then we'll find VC. Looking at this circuit, these two components, now it's great that they're there. No current flows through the resistor, so there's no voltage drop across it. Oops. And then the voltage source, we don't actually care about anything over here. I can remove that as well. So the result is I can redraw my circuit. It's even easier. Assuming it's steady state, my capacitor becomes an open circuit. I want VC. This will be my 0 minus. Now this one I can just read off because the positive and the positive match. VC at 0 minus equals 120 volts. And because of the equation, VC at 0 minus equals VC at 0 plus equals 120 volts. So this term in the equation, VC at T naught, with switching time will actually just be 120. So VC at T naught is 0. I can keep it as that. So it's technically the plus and minus. VC at 0 equals 120 volts. So that's this part of my equation solved. Now the next easy thing to do should be to find, actually we gotta draw the circuit t greater than 0. For time greater than 0, this is where the most of our analysis will come into play. We need to find this, what's the final value, VC at infinity, and we need to find that's tau, which is dependent on what is R. So let's find what is R. It's the Thevenin, I misspell it every time I write it. Thevenin circuit from the capacitors perspective. So we're going to redraw the circuit. Now the switch is closed. So I'll still draw the other side in there, but that's now not connected. I have my capacitor, VC across it. Now that's closed there, 10K. And we have a voltage source, 10 volts. Okay, now what do I mean by take the Thevenin circuit from the capacitor's perspective? So I'm going to open up the capacitor. Oops, wrong color. So the capacitor will become just open circuit. I still have the 10K resistor. And then because it's Thevenin, I'm going to short circuit the voltage source. If it was a current source, I would open circuit it. And then if we notice, the other side of the circuit here, this 120, doesn't actually matter. It's because it's not connected and we're not looking for a voltage across it. There's no information there I need, so I can get rid of it. So this is what we have. And then what is R Thevenin? R Thevenin, looking into here, well, this one's an easy one. There's a single resistor. RTH equals 10K. Now, what is tau? Tau equals RC. Now for that, I'll sub in the values. R, 10K. C is 100 microfarads. So 100 times 10 to the minus 6. And to calculate this, I'm going to use my calculator. 10 times 10 to the 3. That is 100 times 10 to the minus 6. Showing you what you should put in there. And this will equal 1. Oh, that's actually quite convenient. I came up with the numbers just off the top of my head. So tau is 1. So that's another part of the circuit, or the big equation, that we determined. Last thing we need is this VC at infinity. So let's solve for that now. So VC at infinity assumes that the circuit is in a steady state. What's different from the steady state before that we already solved, was the first steady state we did was actually before the switch activated, right? It's in this position. Where is it? Right there. But now the switch is moved to the next position. So it's changed the structure of the circuit. So the steady state will be for this circuit here. And I got my capacitor, plus or minus VC. Switch is closed, 10K, plus or minus 10 volts. Now, as before, I'm not actually looking for anything on this side of the circuit. I don't care, so I can just take it out. And all I'm left with is this.